In this video, we'll learn about blackbody radiation. We'll begin by looking at blackbody radiation basics, then we'll learn about intensity wavelength graphs and Wien's displacement law, and we'll finish up with the Stefan-Boltzmann law for blackbody radiators. Let's see the basics. Earlier, we learned about thermal radiation, which is one of the three ways in which thermal energy can be transferred. We discussed that all objects are able to absorb and emit energy in the form of electromagnetic radiation, in other words, as photons. You might have observed that on hot sunny days, dark objects heat up much faster than bright objects. For example, if you want to stay cool, it is better to wear a white t-shirt instead of a black t-shirt. Now, this observation suggests that darker surfaces are better at absorbing and emitting radiation than brighter surfaces. So while darker surfaces tend to absorb radiation, brighter surfaces tend to reflect radiation. In physics, we often talk about the blackbody radiators, and here is how a blackbody is defined. A blackbody absorbs all the wavelengths of the electromagnetic spectrum that fall on it, and it does not reflect any of this radiation. Similarly to other concepts in physics, a blackbody is an idealization that does not exist in practice, although some objects are very close to being perfect blackbodies. Keep in mind that on IB exam questions, certain objects, for example stars and planets, are often assumed to be blackbody radiators. So simply put, blackbody radiation is electromagnetic radiation given off by a blackbody. Since blackbodies absorb and emit radiation at all wavelengths, the wavelength spectrum of blackbody radiation is continuous. We'll now move on to learn about the intensity of blackbody radiation along this spectrum. Intensity might mean slightly different things in different contexts. Here we'll define intensity as the power emitted per square meter. We can express this definition through the following formula. The variables are summarized in this table. From the definition, it logically follows that the unit of intensity is watts per meter squared. Now we are ready to discuss how the relative intensity versus wavelength spectrum graph looks like for blackbody radiators. Different blackbodies, for example different stars, have different temperatures. The first intensity versus wavelength graph that we'll draw will be for a blackbody that has a temperature of about 6000 Kelvin. Note that this temperature is very close to the surface temperature of our Sun, which is about 5800 Kelvin. So to plot the graph, we measure the radiation intensity at different wavelengths using an instrument called a spectrometer, and then we simply plot the results on our graph. This is how the graph looks like. As we mentioned, the temperature of this blackbody is 6000 Kelvin. Let's plot two more graphs. One for a blackbody at a temperature of 5000 Kelvin, and another for a blackbody at a temperature of 4000 Kelvin. The visible part of the wavelength spectrum is located approximately here. Let's discuss a few key points. The graphs are close to, but do not actually pass through the origin. As you can see, there's a steep intensity increase before the peak. After the peak, intensity decreases and approaches zero. And finally, as temperature increases, overall intensity increases, and the peak is shifted to the left. A key feature to keep in mind here is that on the vertical axis we have relative intensity. In other words, the graphs do not show specific intensity values in watts per meter squared. Instead, they tell us how the shape of intensity graphs for blackbodies at different temperatures compare to each other. The peak of each graph shows the specific wavelength where intensity is a maximum for a given temperature. To make the connection between this peak wavelength and temperature, we'll now turn towards Wien's displacement law. Here are the relative intensity versus wavelength graphs that we've just drawn. What Wien discovered was that the height and the width of the intensity wavelength graph depends only on the temperature of the blackbody radiator. The full version of Wien's law allows us to calculate the wavelength at any point along the curve. In the IB physics course, we only use a simplified version of this law that allows us to calculate the peak wavelength. Here is the peak wavelength formula, along with the variables. Let's apply this formula to calculate the peak wavelength for the blue graph, where temperature is 6000 Kelvin. Rearranging and substituting, we get that the peak wavelength is equal to 2.9 times 10 to the power of -3 divided by 6000. Carrying out this calculation gives us approximately 4.8 times 10 to the power of -7 meter. We can also give this answer as 480 nanometers. Note that this wavelength is in the visible section of the electromagnetic spectrum, and its color is somewhere between blue and green. Using the temperature and the surface area of a black body, we can calculate the total power that it radiates. Let's see how we can do this by learning about the Stefan-Boltzmann law for black body radiators. Stefan and Boltzmann, two different scientists, independently derived the following formula for black body radiators. Here is how the variables in this formula are defined. Note here that the total power radiated by a black body is also called luminosity. Now, power radiated is the same as energy radiated per second. Since the total surface area of the black body is A, we can conclude that the energy radiated each second by 1 square meter of a black body is sigma, so the Stefan-Boltzmann constant, multiplied by the absolute temperature to the power of 4. With this, we have completed our learning about black body radiation.